This is section 9.2, and this is on simplifying radicals. So as we talked about in the last section, this symbol right here is called a radical. Now you might look at it and say, no, that's a square root symbol. You're correct. If this radical has no index written right here, that is a square root. However, we know that you can put like a little 3 right there and make it a cube root. And then in the future, we're going to see that you can put like a 4 on there, make it a 4th root, 5th root, all kinds of stuff. But this symbol is just referred to as a radical. Now, a couple of properties we're going to get out of the way here. First one is that the square root of a product is equal to the product of the square roots. So this means that if you have the square root of two things being multiplied, you can split those up into the square root of the first and the square root of the second, and then multiply those answers. You can also do this for division. You cannot do this for addition or subtraction. Okay? You cannot take the square root of 9 plus 16 and do the square root of 9 plus the square root of 16. It doesn't work that way. Alright, so a square root is said to be in simplest form when the stuff under the radical has no perfect square factor. Now, let's just review what a perfect square is. A perfect square is this list, and it's the result of a number squared. So 1 is 1 times 1, or 1 squared. 2 squared. 3 squared. 4 squared. 5 squared. And so on. So these are what's referred to as perfect squares. Okay. So let's talk about simplifying square roots. Now we're not talking about approximating them, so don't get that confused with what we did in the last section. We're not approximating these, we're actually giving the exact answer in a more simplified form. So what we can do is split 40 into 4 times 10. Now why did I think I split it into 4 and 10? Why didn't I split it into 8 times 5? Right? Or 2 times 20. Why 4 and 10? Well, because 4 is a perfect square. So my goal is to split these up into multiplication where 1 or more, if possible, but usually just 1, is a perfect square. Because we know from those previous properties that if I have this product in here, I can separate that square root into the square root of 4 times the square root of 10. We know the square root of 4 is just a nice little 2, and that square root of 10 comes down. We don't have to write this multiplication. We know that this smushing right here does imply multiplication. So this is the simplified answer here. This square root of 10, this 10 is completely simplified because 10 doesn't have any perfect square factors. I'm not saying it doesn't have any factors. I'm saying it doesn't have any perfect square factors. Yeah, 2 and 5, but neither of them are a perfect square. Now, the nice thing about this is the calculator that we're using will do this for us. The 83 and 84, I don't think do these. But this nice little TI-30, oh yeah. So if you do the square root of 40 and you hit enter, boom, 2 root 10. That's great, isn't it? Yeah, I love that about this calculator. Okay. The square root of 48, again, you can use the calculator for it. If we wanted to do the square root of 48, you can see it's going to be 4 root 3. But if you want to see the behind the scenes action here, that's because 48 splits into 16 times 3. Then that square root of 16 over here simplifies to be 4, and then that root 3 comes down. I don't think that this calculator will simplify cube roots, so that's why I'm showing you with square roots. Even though the calculator does these, I'm showing you how this works with the square root so that when we get to the cube roots, it might make, you'll see those connections. Now, some people will simplify the square root of 48 in a slightly different way. Okay, this is all optional here. We do have the calculator that does it for us. If for some reason you didn't see that factor of 16, if you split this into 4 and 12, and you said, oh, the square root of 4 is 2, and then we get the square root of 12, this is not simplified completely. I mean, it's better than it was, but 12 has a perfect square factor. So then you would have to take this 2 root 12, split 12 up into 4 and 3. The square root of 4 is another 2. So all of this over here is just to show you what would happen if you took a different approach to this root 48. But if you followed what I did, you know how to do it on the calculator, then just pretend this never happened. Okay. The square root of 50 simplifies to be 5 root 2. Now at this point I'm going to show you my shortcut when I do these. Okay. When I split these apart, you can see I kind of use what looks like a little factor tree here. So I split 50 into 25 and 2. Not 5 and 10, I split it into 25 and 2 because I know 25 is a perfect square. And then I took the square root of 25, and it's 5. So I circle that as a reminder to myself that this is going to be on the outside of the radical, this is going to stay under. So this is just my own personal abbreviation for this. It's just a little shortcut so that we don't have to write quite as much. If you feel more comfortable with writing the steps out, that's cool too. Okay, so the square root of 75 over 16. Remember, with division we can also split these radicals apart into the square root of the top and the square root of the bottom. The square root of the bottom, square root of 16, that's just 4. The square root of 75, I'm going to go over here and do a little side work. 75 splits into 25 and 3. So the square root of 25 is 5, and that root 3 is just along for the ride. So this top stuff of square root of 75, this numerator in here, that simplified to just be that 5 root 3. The 4 came from that square root of 16. Now I'm not really sure if the calculator would simplify this one, so let's just see what happens. Oh yeah. Yeah, it's not going to do that one. I didn't think it did. So fractions like this, when you have these square roots of fractions, your calculator's not going to simplify those. However, we can circumvent this a little bit. We can get around this. Check it out. The square root of 75, 5 root 3. Square root of 16, 4. So if you know that this division, that you can separate it into the square root of the numerator and square root of the denominator, then you can do these individually on your calculator. Okay, moving on to the cubes. The perfect cubes are these numbers. They come as a result of 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and so on. So just like with the square roots, we're going to simplify the cube roots in the same way. We're going to split this number under the radical into pieces, one of which is a perfect cube. So for 24, I didn't pick 6 and 4, or 2 and 12. I picked 8 and 3 because 8 was one of those numbers from my list of the perfect cubes. So then I can split this up into the cube root of 8 times the cube root of 3. The cube root of 8 is just more simply written as 2, and then this cube root of 3 along for the ride. Now I got to refresh my memory here, but I'm pretty sure that this calculator does not simplify cube roots. It does not. It does not give you the exact value for these. Now, if you wanted to do the cube root of 8, it will simplify these if you end up with that nice integer answer. So it will do the square roots for you, but the cube roots you're going to be on your own. So these are going to be a little tougher. Okie dokie. How about the cube root of 135? So for this one, you might find it helpful to just keep that list of these perfect cubes handy and just start dividing into 135 and see which one goes into it. Right? So I mean, like 135 divided by 8. Okay, yeah, no, that's not going to work because it's not a whole number there. 135 divided by 27. Ooh, 5. So there you go. So I just take that number to the radical and I just start dividing it by those perfect cubes until I find one that's going to give me, that's going to divide in without a remainder. And I know it's not going to have a remainder because see how it's got that 0.875? That's the remainder. All right, so we get the cube root of 27 and then we get the cube root of 5. Cube root of 27 is better known by its friends as just the number 3. This is just along for the ride, so there's my more simplified cube root there. Okay, the cube root of negative 96. This one's tricky because of the negative, but remember we can take the cube root of negative numbers. So 96. I start off, like always, just trying to divide out some perfect cubes. 96 is divisible by 8, so I split it into 8 and 12. Now, I put the negative on the 8 because I knew that I could take the cube root of that negative 8. Remember, I can't take the square root of a negative number, or I'm going to get an imaginary answer. But I can take the cube root. So just to refresh your memory here, we have to hit 3, and then the cube root, and it's in green above this little up arrow. And if we did the cube root of negative 8, we get negative 2. Now, the cube root of 12, nothing we can do with that. The square root of 12 we can simplify further, but not the cube root. The cube root of 12 here, 12 does not have any perfect cube factors. Like 8 doesn't go into it. 27 doesn't go into it. Okay. Now, here's what we're going to be able to assume. We're going to assume for the remainder of this semester that x is going to be positive or 0 for these, okay? That's important because then if you take the square root of x squared, you're just going to get x. That's always true as long as x is greater than 0. So for instance, the square root of 5 squared, that's the same thing as the square root of 25, which is just 5. So what we can kind of think of is this square root and this squared as being inverse functions and undoing each other. Right? So it's saying, hey, if I've got 5 and I square it and then I take the square root, basically whatever I did to 5, I just turned around and undid it. So I end up right back where I started at 5. Now that's going to be important because now we're going to simplify radicals that have variables to them. All right. The square root, I'm going to give you a shortcut, okay, don't worry. But the square root of x to the 6th, I could rewrite x to the 6th as x squared times x squared times x squared. Then I could take the square root of each one of those. And remember, the square root and the square undo each other. So if that squared and that square root undo each other, I just get x out of each one of these 3 factors, and then x times x times x is x cubed. Right? Easy peasy, right? No problem. All right. So x to the 8th, all right, x squared times x squared times x squared times x squared. So taking the square root of each one of those, that square root and that square undo each other because we're making that assumption that x is positive or 0. So we get x, 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 which is x to the 4th. Now, that's going to be tedious. If I ask you to find the square root of, say, I don't know, x to the 84th power, right? Check it out here. Look at that. I start with an x to the 6th, ended up with a 3. Started with an 8, ended up with a 4. Looking a little sus, right? Is there a shortcut? You bet there is. when you take the square root, you can take this exponent right here, that 14, and just divide it by 2. That's because the square root is really the 1/2 power. But yeah, so we can just divide that by 2 and we get 7. Check it out. 6 divided by 2, 3. 8 divided by 2, 4. 14 divided by 2, 7. Right? So much nicer than all of this garbage. Right? We're not doing this anymore. We saw the long way, and now we have seen the light. All right, so here's what we're going to do. A little bit more complicated expression. We got the square root of 16x squared y to the 10th. I can split all these apart into 3 different factors. The square root of 16, the square root of x squared, and the square root of y to the 10th. The square root of 16, that's just 4. The square root of x squared, well, we already know what's going to happen with that one, right? We know that that square root and that squared are going to undo each other, and I'm just going to get x. But what if you use this shortcut? What if you say, oh, well, I'm just going to take this right here and I'm going to divide it by 2. Okay, 2 divided by 2 is 1. Same answer. All right, here, 10 divided by 2 is 5. So we get the answer 4x y to the 5th. Don't write that 1. Hawks considers that to be unnecessary. If you try to write that 1 exponent, Hawks is not going to mark it wrong, but it is going to tell you that your answer is not simplified. So, picky patty here. Okay, now what happens if the exponent is an odd number? That gets a little bit trickier here. So if we get this odd number, x to the 7, I'm going to show you the long way, and then I'll show you the shortcut. So the long way is to rewrite it, x squared, x squared, x squared, x. I picked these x squares because I know that the square root of x squared, those undo each other really nicely. So in doing that, I get that 3 of these x squares get undone. But then I've got one little square root of x here that doesn't have a squared, so that square root of x is just going to stick around. So I get x cubed, and then I get this square root of x. Okay, so let me show you what happens. If you take this power and you divide it by 2, that's because it's a square root. So 7 divided by 2, right? So here's the long division. If you divide 7 by 2, 2 goes into 7 3 full times, and you have a remainder of 1. This 3 is your outside power. Your remainder is your inside power. Now, when you go to put this in Hawks, of course, don't write that 1. Because it's going to tell you it's not simplified. Don't write that 1. So I should probably say don't put that 1 in Hawks. So our shortcut for this is going to be, if you're simplifying the square root of an exponent, you can divide that exponent by 2. The quotient is your outside exponent. The remainder is your inside. And I say inside, I mean like under the radical is what I mean by inside. So there's the stuff that I just said. So let's look at x to the 25th. All right, so I'm going to take 25 divided by 2. If you did want to write out all the details here, you can. So 2 goes into 25 12 times with a remainder of 1. If you can do this in your head, that's awesome. Okay? If you have to do a little bit of side work, that's okay too. So 25 divided by 2. So 2 goes into 25 12 full times, and you have a remainder of 1. That means the 12 is going to be on the outside, the 1 is going to be on the inside. For Hawks, you're going to write that as x to the 12th and then the square root of x. Okay. So next up here we have the square root of x to the 15th, y to the 20th. I did these in different colors just to show you I was doing the same thing. but just to show you where all the numbers end up going. So for this 15, I did 15 divided by 2. So 2 goes into 15 7 times, right? Because 7 times 2 is 14. You subtract, you get a remainder of 1. Okay, so we get x to the 7th. There's the remainder of 1. The 20, when you divide it by 2, you get a 10, but no remainder. All right, well that just means you're going to have y to the 10th and no y. So no remainder means you're not going to have a y left under the radical. So it means no variable under the radical. Okay, so these are just going to get a little more menacing, but our process is going to stay the same. Okay, my process is always dividing by 2. Why am I always dividing by 2? Because this is a square root. When we get to the cube roots, I'm going to divide by 3. If you do a fourth root, I'm going to divide by 4. Okay, so the square root of 9x to the 13th all over y to the 12th, or 10th, sorry. I'm going to split these 3 up into 3 separate square roots. The square root of 9 is 3. The square root of 13, or sorry, x to the 13th. All right, divide that by 2. How many times does 2 go into 13? Goes into it 6 times. Right, so I'm just kind of, let me grab a red pen. Here's red. So in my head, I'm doing 2 goes into 13 6 times. 6 times 2 is 12. You subtract and get a remainder of 1. So that's what's going on in my brain, where that 6 remainder 1 comes in. So there's the 6, there's the remainder 1. For the denominator, I get this y to the 10. So 10 divided by 2 is 5. No remainder, so nothing left under that radical. So just get a plain old y to the 5th. Remember, we're not going to write that 1, my final answer. So here we go. Okay, next up, the square root of 32, a to the 9th, b to the 11th. Like I did last time, I'm going to split these into kind of 3 separate smaller problems. The square root of 32, it's not as nice as the square root of 9, is it? This is like example 1, where we got to split that sucker into pieces. You can use your calculator and do square root of 32 and get 4 root 2. So there's the 4 root 2. The square root of a to the 9th, 9 divided by 2 is 4 with a remainder of 1. So there's the 4, there's the remainder 1. 11 divided by 2 is 5 remainder 1. 5 remainder 1. Now be careful over here. Don't take 32 and divide it by 2. Okay, don't do that and get 16 without a remainder. No. That's only for these exponents that I'm doing that. That's my shortcut for simplifying exponents. If you're simplifying just a number and it's not an exponent on a variable, don't do this dividing by 2 business, okay? All right, so now pulling all this together, all the outside stuff gets smushed. 4, a to the 4th, b to the 5th. And then all the inside, the under the radical stuff, that gets smushed. So we get square root of 2, a to the 1st, b to the 1st. Remember, we're not going to write those ones because Hawks is picky-patty about it and doesn't want to see all that unnecessary stuff. Next up, very similar to the one that I just did. I'm just going to try to cut out some of those steps. If you still have to write all those steps, it's okay. I'm just going to try to do this one very similar to the last one, but with just a little more explaining, a little less writing. The square root of 12, you can use your calculator and get 2 root 3. Or you can split it into 4 and 3 and take the square root of 4 and get 2. This exponent of 6 divided by 3, we get 3 remainder 0. So there's my 3. Remainder 0 means there's no m left under the radical. 7 divided by 2 is 3 remainder 1. Now, again, all these, in case you're wondering, like, how does she keep getting this 3 remainder 1, 3 remainder 0? This is just long division, okay? 2 goes into 7 3 times. 3 times 2 is 6. You subtract, you get a remainder of 1. There's nothing complex happening here, okay? So I don't want you to assume that there's something, really complicated going on, all right? So, and if at any point in any of this you don't understand what I'm doing, you can always just like send me a picture of this and say, hey, can you explain a little bit more, what was going on in here? And I'm happy to do that for you. All right, so we get that 3 remainder 1. So there's the 3. There's the remainder 1. So there's my final answer. Of course, you don't want to write that 1 in Hawks when you put this answer in. All right, let's extend this now to cube roots. So for square roots, we had that happy little shortcut where we just divided by 2. Because it's now a cube root, we're going to divide by 3. Okay, don't worry about that 3 out there. All that 3 is doing is telling you that it's a cube root problem. Okay, that's not a 3 that's going to be like on the outside of the radical, like brought along. It's not like a 3 times the square root. That's just a cube root. We do have to continually write that cube root. But just to show you, the shortcut still works. 12 divided by 3, you get 4. If you wanted to do this the long way, which I'm sure you do not, you can split these all into a bunch of x cubes. The cube root of x cubed, those are inverses of each other. And each time those cancel out, and we get that x to the 4th power. Okay. So to simplify square root exponents, you divide by 2. To simplify cube root exponents, you divide by 3. So let's see what's about to go down here. The cube root of x to the 16. All right, so we're going to divide 16 divided by 3. And I just kind of did the little side work over here. 3 goes into 16 5 times. 5 times 3 is 15. Subtract, you get a remainder of 1. Outside, inside. Don't forget to put the cube root symbol here. That's important. Don't write x to the 5th, the square root of x. You need that cube root symbol on there. So we get x to the 5th and the cube root of x. Y to the 23rd. Take 23, divide it by 3. We get 7 with a remainder of 2. So 7 is my outside power, 2 is my inside power. Don't forget the cube root in here. This shortcut is pretty darn sweet, isn't it? Yeah, it is. Okay, let's look at a few more. I try to give you, a lot of examples so that you can have a lot of comparisons when you're doing these, not to bore you for 30 minutes. Okay, so the cube root of 125 is 5. You can do that one on your calculator if you want. The cube root of m to the 144, that's an exponent, so I'm going to divide it by 3. I get 48, no remainder. I just did that on the calculator. How do I know there wasn't a remainder? Because there wasn't a decimal part to it. It was 144 divided by 3. So it was just 48, not 48.33333 or anything. All right, so cube root of 125 is 5. Divide that out, we get m to the 48, no remainder. So I don't have any m's left under that cube root. So I don't have a cube root in my answer. All right, this next one. Now we're starting to get a little more complicated, but I'm trying to break this into smaller pieces for you. So you can see like the red stuff is one part, the green stuff is another part, and then you kind of pull those together for your final answer. Okay, so a to the 4th. 4 divided by 3, that's 1 with a remainder of 1. So check it out. 1 exponent, remainder of 1. B squared. Ooh, 2 divided by 3. This is messy. Right? Because you may be like, wait, 3 doesn't go into 2. Don't divide 2 into 3. It's 3 divided by 2. Or sorry, it's 2 divided by 3, so it's 3 going into 2. How many times does 3 go into 2? It doesn't. So it goes into it 0 times. 0 times 3 is 0. Subtract. you get 2. So what this means is since this is a cube root, every b to the third can essentially be taken out. Here I don't have any b to the thirds that I can take out. So I get the 0 remainder 2. So 0 remainder 2. Remember, b to the 0 is the same thing as 1. That was back in Math 90. We had some exponent rules that, yeah, you know what, that I will give you in the next section. I'll give you some exponent rules, like a little formula sheet to use just to have handy when you're doing these. But b to the 0 power is just 1. So I can just replace that. Not b to the 1, just 1. So that's going to be a to the first. B to the 0 is just 1. I didn't put a 1 right here. And then we got a cube root of a to the 1. Don't write that 1. And then b squared. I realize that one was pretty messy. But not as bad as this last one. Look at that. That's a hot mess, isn't it? That's cool. We can do this. It's just a bunch of dividing by 3. 6 divided by 3 is 2. No remainder. So no x's left under here. 7 divided by 3 is 2, remainder 1. 2, remainder 1. 9 divided by 3 is just 3, no remainder. If there had been a remainder, then I would have something left under that cube root radical there. So when you put this in your final answer, don't put that 1 right there on that z. Okay, so this does finish section 9.2. Sorry, I know this was a really long video. Thank you for your patience. So, all right, this concludes section 9.2.